Hello, ladies and gentlemen. Herzlich willkommen. Добро пожаловать, друзья. My name is Andrei, and now I will record a new session regarding advanced mesh generation with Snappy and cfMesh. We will research the new geometry. As you can imagine, it will be an airplane Antonov AN2. This is a legendary airplane which is used until now and helps people to arrive the places where no road has been built. I also wanted to investigate this airplane because there are some technical detailed drawings and documentation of it to find in the internet. Let me show you some of them. Here you see the general arrangement, then you can find something about rotor, about the wing. Also you can see the main dimensions, and these three drawings are detailed drawings. Traditionally, after creating the geometry, we convert the original CAD file to step and start the Salome in order to create the boundaries. Let me do this, and I go to the work directory and run the Salome. It starts in a few seconds and we will begin. I have to define the folder and open the existing case. It will be AN2, Salome, steady simulation, and simulation 1 and 2. Have a look on this geometry. The geometry of Antonov AN2 is very special and difficult. I tried to reproduce the motor cooling ribs and show you the maximal possible resolution of such fine geometry in reality. You can see the motor ribs, cooling ribs. Here they are. The problem of such research is indicated by limited power of the workstation. I know the openFOAM and my workstation can easily calculate the meshes with a large cell number up to 140 million hexaedra cells, but in this case I get the problem of overload the graphic processing unit, the GPU, by visualizing of meshes with more than 100 million cells. Let me concretize the problem. For better understanding, I created the image in Paint where I will describe the problem. You see the cylinder geometry of motor fine walls with cooling ribs. The main dimensions are: the diameter is 1.4 meter and the length is 0.2 meter. It is defined also in the equation: 0.1 length and diameter 1.4 millimeter. I also can show you this geometry part in Salome. You see this part? This is the motor cooling area. So the thickness of created ribs is 4 millimeter. Original thickness of the rib must be close to 1 millimeter. If I want to create the mesh on the ribs, I have to keep 1 or 2 cells in thickness direction. Let me show you. Here, for example, we have the rib thickness is 4 millimeter, and each cell will be 2 millimeters, so that I have two cells in thickness direction. If I take this dimension of cell size, I get in all 38 million cells in this motor section. In origin thickness of the rib, I would like to take only one cells in the thickness direction. The cell size will be 1 millimeter. For example, here below, the rib thickness is 1 millimeter, and we will take only the 1 millimeter cell size here. With this cell size, I became more than 300 million cells. In this case, the RAM memory and the CPU will be overloaded. Let me show you. It will be here more than 300 million cells. So I have to let the thickness stay as it is, 4 millimeter, and define only two cells in thickness direction, so that the cell size will be here 2 millimeter. This will be a simplification of the model resolutions. So this was an example of how to define the cell size before the meshing begins. Now let me switch back to Salom and show you the whole geometry. Now we have to go through the Salom and extract all boundaries. Before we give the names to each boundary, we have to look on airplane parts definitions. Let me show it in internet. Here we can find airplane parts in Russian, in German, as well as in English. We will take the definitions in English. In our case, we have fuselage, wings, flaps, horizontal stabilizer, elevators, wheels, rudder, tail, and motor. Let's keep the names in mind and give the correct names to each boundary in Salome. So for that, I have to go to imported part-1. Go with the right mouse button to create group and choose the rectangle section, and after that I have to extract all necessary edges and give them the names. For example, we have elevator, add, show only selected. This will be an elevator. We will write walls, wing 3, horizontal stabilizer, elevator, apply and close, and do the same thing for each part of the whole geometry. For example, we can define the horizontal stabilizer here as it is, then the rudder, then we define wheel, rear wheel, when the tail is defined, fuselage rear. So the next part will be the front fuselage, The same I will do with the front geometry. It will be step part 2, this one. Now I go through all defined geometries. It will be walls, wing 1, flaps, this geometry part. The next one will be wings, flap for wings 2. You see the bottom wing. Then it will be the top wing 1. The second one is the bottom wing walls. Then we have to define the walls wheel front. We go forward to fuselage front. Look at this. And of course motor fine and motor geometry boundary. Let me show both geometry steps. At the end we define the inlet and outlet and walls for air border or air limit. For that I imported the bounding box. You will see that the bounding box is divided into inlet part, outlet part and walls box. All of these boundaries I will export. One of the lastest operations here in Salom will be the export of boundaries as STL files. So I take all boundaries which we have already created and export them as STL. For that I have to create new folder, export, and now I have to export all of these boundaries. Here you can also change the settings for ASCII or binary, relative size or absolute cell size. I will cancel it because I've already done this. Now I want to show you the change geometry of Antonov AN2. This geometry is original one, and here I turned the wings into 15 degrees. You see that the length of global length of wings is the same, but one geometry, the changed one, show you with the wings are turned to 15 degrees. In this case I have also to define all boundaries and give them the right names. Let me do this or show you how the names and boundaries are calling. At first we start with elevator, then we will show, when I show the horizontal stabilizer, the rudder fine, when the wheel in the rear, tail, and of course the fuselage. The same on the geometry part 2. Flaps bottom, walls top walls wing bottom, wheel fronts, and fuselage front. I don't extract here the motor fine and motor boundaries because they are the same as in previous geometry. So in that case I have only to export these parts in a separate folder. Export STL, and here I will export them, all of them. Let me explain you why we extract all of these boundaries and do not take them as one part, as one wall part like this. Why we don't do that? You have seen the resolutions of cooling ribs on the motor fine here. If we take the same resolution for all parts, we get more than 300 million cells and overload our RAM memory or graphic processing unit. Last thing I wanna do in SLOM is to define the bounding box and remember the min max values for all coordinate axes. For that I visualize the bounding box and go to inspection, dimension, bounding box. I take this geometry and let us remember in X direction we have -30 and plus 70, in Y direction -30 and plus 30, and in Z direction -20 and plus 20. So I click apply and close, and that this last part is done. So now I have to prepare the dicts for meshing in Snappy and cfMesh. For that I open my Excel tool, preform template, and also I have to copy all exported parts, for example here, to preform template folder. Export, steady, origin, export. Here we are. And now I have to open the work directory. I start as usually with definition of export folder path. For that I have to go to AN2 STL, steady, origin, export, copy the path, give them here in the cell B1, and click prepare STL files. You see all boundaries are listed here, and of course at the end you will find here the definition. Inlet is number 1, outlet is number 2, and all walls are the number 3. Now I have to define the block mesh. For that I go to snappyHexMesh dict and go to the top. As you remember, or if you are keep in mind, that the bounding box coordinates will be for x -30 plus 70, then for y direction -30 and 30, and for z directory -20 and 20. So the number of cells over the bounding box will be also 5 cells. After the min-max coordinates are given, I look for the global cell size, which codes the number of cells on the block mesh dict in total. It should be close to 1 or 2 millions. So now we have the global cell size 128, and we get here more than 114 millions. I have to look on the second on this line, and here if I want to keep the number of cells close to 1 million, the global cell size will be 621 millimeters. For that I choose 512 millimeters. Let me show the refinement levels of 512 millimeters as global cell size. We go to bounding box, and here we have levels, refinement levels, and meaning of them in millimeters. So it's very good to have the cells 512 because it is integer and is also derivative of the number 2. Also, the number of cells in the block mesh dict will be close to 2 million, and it's enough for me because I want to keep this number between 1 and 2 million cells. Now I have to go through all boundaries and define here the resolutions of it. For example, on inlet I will stay the resolutions of 0, 0, as well on edge refinement, as well on face refinement level. Wall box will be also 0. Fuselage front will have the resolution 0 meter from the face or from the edge, and the resolution will be 5. That means the cell size, min cell size, will be 16, and here it defines 5 to 5. The face resolution will be 5, 5, so that means everywhere on the face the cell size will be exactly the same. The same situation on fuselage rear, I will define 5, 5. The next is motor. Here I define 0, 6, and on the face 5 to 6. That means that the coarsest mesh will have the refinement level 5. And step by step I will do it through all STL files. What I have forgot to say here, why I use the refinement level, for example, for tail 6, for rudder as 7 maximal refinement level. Now I can show you in Salom. I use the method. Here you can go to inspection and basic properties, and here you can see all your minimal edges. I know the geometry because I had created the geometry, and I know that the smallest edges are on elevator, for example, length 8 millimeter. The same, the resolution for 8 millimeter will be 6, so I have to keep 6 for elevator. So the same situation is here given on flaps 8 millimeter. Here we have on the bottom as well 8 millimeter. That means we have everywhere on each smallest face or edge 2 cells. Resolution for each boundary is done. For example, we have here motor fine, the edge refinements, rudder fine, tail, flaps, and also the min and max refinement level for refinement, face refinement. Now we go back to Snappy HexMesh dict, and we have to disable all refinement objects except refinement box. So here we can write here false on cylinder, false on refinement sphere, false on cone, and false on the hollow cone. I have to define also 3 instead of 3 refinement objects. The dimensions I will take from here. So minus 15, minus 20, minus 10, so the min, 70, 20, 10, refinement level 1, then we have minus 6, minus 15, minus 5, and 30, 15, 6. The second one, refinement level 2. The last one, minus 2, minus 10, minus 3, 20, 10, 5. Resolution will be 3. We copy this value, make the resolution 3 and comment it as a refinement level 3. Now I go back to the front and start and go forward with surface feature extract dict definition. The surface feature extract definition, here I let everything as it is, include angle 179, write objects no. Decomposer power, we have to define here 16 processors. I have in X directions 4, in Y direction 2 processors, and in Z direction I have 2 cores. So that the total number of processors will be 16. I choose the method scotch and go forward to snappyHexMesh dict begin. It's true, and I want to create castellated mesh. I want to snap. I don't want to create a boundary layers. It's not interesting for me. Merge tolerance will be 1A minus 6, debug will be 0, geo tolerance 1A minus 4, refinement mode global and mode inside for each of refinement box. Refinement regions we already defined, it will be only a refinement box. Then I go forward with max global cell size. I prefer here to take 100 millions, and for each processor we have 6,250,000 cells. So number min refinement cells we have 10, max load and balance 0.1, number sense between the levels I will keep it to 2, I will decrease it to 2, features true, refinement surfaces also true, resolve feature angle 30 is planar angle, location in mesh. So location in mesh will be 20 0 0. Let me do it to 0. So I can show you only where it will be. It will be after the tail or rudder of the airplane. The total length of airplane is approximately 12-13 meters, and 20 will be in it here. So allows three standing zones false. Our location outside mesh will be the point inside the airplane. Now we go to snap control. I'll let everything is as it was in previous snappyHexMesh dig defined, everything as it is. The add layer controls I don't need because we have here add layers false. So when I only need to define the mesh quality settings, and here I will define the default settings. So this is done, bounding box is done, so I can go to STL files and keep it safe, and then I create a snappyHexMesh dict. It's done. cfMesh translating is also ready. I go to cfMesh. Right here everything is false and except a refinement box false. Creating the mesh dict false. So the rest will be as it is. I only have to copy this cells to refinement box. So this is a definition of our box, refinement box. What I have to say here, that we have for the first box with refinement level 1 approximately 3 million cells, for the second one 5 million cells, and for the last one will be created over than 13 million cells. Now I can keep it safe, create the mesh dict, our dicts create. So now I copy the created block mesh dicts. Everything I will copy to simulation 1 preform template. Here we do it. I also can have a look on Snappy in order to see if anything is done. So we have here geometry, everything seems good. The number of cells for each refinement box is defined. Here we have 4 million, here we have 5 million, here we have in refinement box 3 with refinement level 3 we have 13 million. Here we have definitions of levels. Mode is inside, as we already mentioned. The maximal number of cell will be 100 millions. Number of cell I will keep to 2. Box refinement features definition and refinement surfaces defined here. Okay, let me location mesh. It seems to be good. Mesh dict also looks good. Then I have to prove what we have here. Course mesh simulation 1 origin has CFD files. Here we are. Salome folder with export. This with a new export and export of HDF file. Preform template is here included. Now I will look on simulation 2. We have CAD files and Saloma with export and HDF file. This is the current export. That's it for this session.